We're going to get started off here with our own Earth and Planetary Laboratories, Alan Boss and John Chambers, who have been staff members for a while now, and they are experts on the field of different ways that planets can form. Alan knows a lot about disks, a lot about gravitational instabilities, and how giant planets might form. And John is an expert on how Pebble Accretion and a new wave of possible core accretion ways that planets can form. So Alan and John are going to start us off talking about basically how we think planets form. There's many different varieties of how they might form, and then the evidence of how these can form is going to come out in the next few weeks. So next week we'll have Scott Kenyon from Harvard talking about how impacts affect planet formation. And then after that, we'll have Bill McKinnon, who's going to talk about how dwarf planets might form, the interiors or structures of the dwarf planets. And then we'll finish off with talking about Juno results in March. So let's start out now with Alan is going to give the first half of this talk, and John will give the second half of the talk. And let's learn about how planets might form. So take it away, Alan.
Okay. All right, so thank you very much, Scott, for inviting us to give this talk. It's very much intended to be an overview for what you'll be hearing from this entire month with the other three talks that Scott just mentioned to you. So we're going to break this up into two sections. I will lead off by summarizing just sort of the big picture of what observations are for planets outside of our solar system. And one of the end-member mechanisms for making gas giant planets called disk instability. And then John will pick up on the second half of the talk and talk about the more conventional methods for making planets based on core accretion and variants like the Pebble Accretion model. So let me first just remind you where we are as of exoplanet discovery space as of 2021. The amazing thing is that 25 years ago, this diagram would have been empty except for the outer planets here in our solar system and maybe a couple of pulsar planets off down near the bottom of this plot. But since then, the advent of Doppler spectroscopy and transit surveys and microlensing and direct imaging have pretty much populated this diagram pretty well. The left-hand side are the hot Jupiters and the hot Earths and super Earths. This is what we usually hear about, but from the context of this talk, these are boring. We don't care about them, which is an odd thing to say, but that's what this talk is going to be focusing on, the objects in the outer solar system. And it looks like from this plot that there isn't much of anything in this region here. I hope you can see my cursor, right? Is that right, Scott? Can my cursor be seen?
Yeah. Yep.
Okay, so the fact that there's not very many observed planets out here, except for some by microlensing, is not because they're not there. It's just because the observational bias is towards, for both transits and Doppler, large masses and short periods. And so this area here will be filled up more completely when the Roman Space Telescope launches and does its its microlensing survey, because microlensing is most sensitive to objects out in this regime here. So we're pretty sure there'll be more objects out there to be found, but at the very least, direct imaging has found a lot of massive Jupiter, multiple Jupiter mass objects out at great distances, because direct imaging has trouble seeing something very close to a bright object. So that's the sort of population we're going to try to imagine explaining the demographics of how they might form. So how do we do it? Let's see here. Somehow, okay, all right. So there are basically two end members for forming giant planets. The original ideas go back to Victor Safronoff and work he did during World War II, when he came up with the idea of if you want to make a gas giant, you first build a big rocky core, and then the rocky core gets large, massive enough that it starts pulling in gas from the disk. And that's how you would form a gas giant planet. The most important advance on that theory, I think, was by Hiroshi Mizuno, who was a postdoc with George Weatherall and me at DTM back in the early 80s. And he just published this paper, which is should be one of the most cited papers for gas giant planet formation by core accretion, where he noted that if you have a 10 Earth mass core and pretty much put it anywhere in a model nebula, regardless of what the background density is or temperature, a 10 Earth mass core is massive enough to start pulling in gas from the disk and rapidly form a gas giant planet. At the time that this was published in 1980, we thought that Jupiter, Saturn, Uranus, Neptune all had roughly 10 Earth mass cores. And so Mizuno's paper seemed to just in one fell swoop say, hey, here's how the gas giant planets formed and the ice giants as well. So it's been a very attractive paradigm for how to make gas and ice giant planets. The alternative scenario is a bit more heretical. It's based on some ideas from long ago by Gerard Kuiper and Al Cameron did some dimensional analysis almost type approach. But this paper from '97 is the first one that really did a full 3D hydrodynamics model. The idea is that instead of going from the bottom up by building rocks, larger rocks, you start top down by having the gas disk itself form clumps through spiral arm formation. If the disk is unstable, which I'll show you in a moment, it can form clumps rather quickly, and those clumps could contract down and form a giant planet. It's important to note that even in this early paper, I pointed out that if you have roughly a solar metallicity, which is about 2% by mass, then a Jupiter mass planet should have roughly a 6 Earth mass core just by having the solids that are inside the dust grains form a core. So even if you have gas giants formed by this mechanism, you should still end up with a rocky core at some point. Okay, just to give you a feeling for what that would look like, here is a movie from an old calculation of mine, but an oldie but a goldie. And what you're going to be seeing here is the evolution of the density distribution in the midplane of a disk, which is about 20 AU in radius. There's the inner 4 AU is blocked out just for computational efficiency. Otherwise, the time steps would be much smaller. It would take longer to go. And this is a fully 3D calculations, but you're just looking at what's in the midplane to make it simpler to reproduce. And you'll see the purplish spiral arms are forming and reforming continually. And sometimes they get dense enough to go through the color spectrum and start turning yellow and orange, and even several times through the spectrum, like that one just went through red and orange. So the clumps keep forming over and over again. This calculation is sort of low resolution, so the clumps can't really survive. They eventually kind of get torn apart by tidal forces. But you can imagine if you have a really well-resolved calculation with infinite resolution, those clumps might be able to survive and go on to become gas giant planets. Okay, so that's the overview. Let me now see if we can get to the next one, which is beginning to talk about observations. One of the very first strong observational constraints that came out was when the first few hundred hot Jupiters were found was that they tended to be found primarily around high metallicity stars. So it's plotted here as a histogram with a number of stars with detected planets as a function of metallicity. Metallicity here is in units where the FU or H ratio, if it's 0, that's the same as solar. Or as it goes up to 3 times solar, this is a log scale. Far right is 3 times solar and far left is 1/3 solar roughly. And there's a very clear distribution showing that as you go to higher and higher metallicity, you're more likely to find a hot Jupiter or a warm Jupiter anyway. So given that higher metallicity presumably means you have more rocks in the disk, and that means you have more building blocks to build planets by the core accretion mechanism. This is taken as basically proof that core accretion is the dominant mechanism for making gas giant planets, which is mostly what we'd found by that time. So that figure is still cited today in papers. I still see it. I wince a little bit because I know that if you actually go to the latest encyclopedia and plot the frequency of planets versus metallicity, that trend is pretty much gone. You might notice a slight bias, sort of a Gaussian, that the right-hand wings are slightly higher than left-hand wings, but overall, that's pretty much looks like a Gaussian. I would not call that a strong confirmation that core accretion is what makes all of these planets. I think the upshot of all this is that you may very well have disk instability making planets as well as core accretion. Or mostly you just can't, this is no longer such a clear distinguishing facet as it was once thought to be. Johanna Toeski has been doing some wonderful work on understanding metallicity, and her work also shows that metallicity is not quite as clear an indicator as it was once thought to be, but it's still something that the observers are working very hard on, especially trying to do an unbiased sample. I think one can claim that this sample must have been biased in order to get that result. Okay, so some other interesting observational results from, here's one from Nuno Santos a few years back, where he just looked at the radial velocity detected planets and plotted their masses as a function of the metallicity of the host star. And looking at the top plot was just sort of the raw data. He thought, well, it looks like there are 2 populations, sort of a bunch down here and there's a bunch up here. And so he says, well, maybe this means that you have 2 mechanisms working. A core accretion mechanism preferentially makes low mass planets with somewhat higher metallicity than solar. whereas disk instability makes more massive planets with a wide spray of masses and metallicities, because disk instability doesn't particularly care about the metallicity of the disk. Protoplanetary disks are typically, if they're massive, they're going to be with optical depths of 10,000 or so. So if you change the number of dust grains by a factor 3 up or down, if you're 3,000 or 30,000, that disk is still optically thick. So disk instability is going to do its thing regardless of what the metallicity is. Whereas, as you can imagine, core accretion really likes to have a lot more rocks around to start building planets. So here's one indication that there may be two mechanisms involved, which is one of the themes of this talk by John and I. We've both been trying to push the idea that trying to make planets by only one mechanism or the other, even though it's good to understand it just for the sake of clarity, in reality, there probably should be a universal theory of planet formation that involves tidbits of both, and maybe even mixtures of the two in the same model. Okay, another bit of observational evidence is from Kevin Schlaufman, one of our colleagues up at Hopkins. He's looking at just transiting planets, again, plotted them with their masses now on the other axis as a function of metallicity. And he noted that there again seems to be two bunches, one here with high masses and one with lower masses. And their metallicity is pretty much, as you can see in this subsample, these are somewhat higher metallicities than on average, but they range over the metallicities. And he proposes that somewhere around, say, 6 Jupiter masses is a critical mass. Namely, if you are above 6 Jupiter masses, maybe you were formed by disk instability, and below that, you would have been formed by core accretion. So it certainly is an emerging view that you really want to invoke both mechanisms to explain the entire exoplanet demographics. Okay, another way of observing things is by direct imaging. It's the tough way to do it. There have only been a few systems found that way, but this one is the most spectacular one of all, around a 1.5 solar mass star, HR 8799. And this is these images actually won the Newcomb Cleveland Award for the best paper in science in 2008. And at this point, by very carefully blotting out the light from the central star, they're able to find evidence for 3 giant planets in orbit. And there's actually in this image, this one here, which is a sort of thought to be a speckle at the time, left over from the starlight. This thing, if you look in the movie next, is actually a 4th planet right here. And this is just the most remarkable movie. This is the first time you've ever seen an extrasolar system with the planets orbiting around the star. That is just absolutely remarkable. But the key thing is the system has a number of multi-Jupiter mass objects orbiting at great distances, and I will show you some models later on in the talk that purport to perhaps reproduce those. Okay, they're also, and that system is fairly old. It's like a 30 million year old star. But with ALMA's advent, we've been able to look at even younger stellar systems. And here's one particular one, Elias 224, where the fact that there are gaps in these disks, here sort of worked out here on the bottom right, these gaps are thought to perhaps be formed by embedded protoplanets. This is the sort of work that Jehan Bey has done such a wonderful job on. These are called kinematical detections, namely that due to the kinematics of having a planet, perhaps you clear disk gas and dust away from you. And in this case, for Elias, there's you see a range of masses here up to, this is rather small, more like closer to Saturn masses, but a couple of multiple Jupiter mass objects out at rather large distances. So we have to be able to have a mechanism that can make large planets at large distances as well as the closer in ones. Here's another even more dramatic recent system that Jehan talked about in the talk a couple of weeks ago, the PDS-70 system with B and C. Again, it's a dusty disk with an artist representation in the lower right. But the key thing is they're not just seeing implications for gap opening, but they actually image B and C here with this Keck near-infrared camera picture, actually seeing the protoplanets. And this is the youngest system imaged to date, I believe. It's roughly 10 million years old. There are several Jupiter mass objects at Beast. They're out at 20 to 30 AU. So this is a classic system that we have to imagine figuring out a way to make. Okay, so how do we make them? Well, first thing you do is you start off with a disk. And what I want to show you is a number of calculations here that all start with a surface density profile, which is given by this curved line here, which is what's being used in this particular paper, as well as the paper calculations I'll show you later on. And it's actually quite similar to the surface density profile that was assumed by Hal Levison in a 2015 paper, where he tried to explain the formation of all 4 gas and ice giant planets in our solar system by Pebble accretion. in a fairly massive disk. Normally, core accretion folks use lower mass disks, but it's hard to get Uranus and Neptune to form that way. And so he started off with a fairly massive disk, which is perfectly fine, but he assumed the disk was quiescent throughout the calculation so that only the pebbles did their thing with each other. Whereas, as you'll see in the calculations that follow, if you do start off with a disk with this sort of surface density profile and a low enough temperature profile, that disk is not going to be quiescent. It's going to start forming spiral arms like you saw in the movie early on. Okay, so here's a set of calculations with that density profile, where what I'm doing is exploring the effects of cooling. One of the key prospects for keeping a disk cool enough to fragment is as clumps are forming, they heat up through compressional heating, and if they don't cool off and lose their energy, they will no longer be able to continue contracting. They'll sort of bounce and form thermally supported objects. So you have to cool the disk. One way of doing it is by putting in a very simple beta cooling formula. So it's seen here on the left-hand side are 4 calculations, all starting from the same disk, but with different initial temperature profiles. We're here, the top one are with a rather cool disk. So it has a Toomre Q value close to instability, which is roughly 1. And it shows that regardless of whether you have fast heating, which is beta 1, or slow heating, beta 100, if you start off with an unstable disk, it's going to go ahead and make very fine spiral arms and clumps. And these are much tinier clumps than you saw in that movie, because this is a much higher resolution calculation, roughly 10 to 20 times higher resolution. On the other hand, at the bottom two shows what happens if you start off with a hot disk and do not allow it to cool, that even if you have rapid cooling, it's still not going to form clumps. So somewhere between these two is the correct value of beta. And the question is, what happens if you start off really hot? Can you actually get to a phase where it cools down enough to start clumping? On the right-hand side shows by the way, once the clumps form and become dense enough, the calculation just can't continue to monitor their contraction. So if one goes ahead and replaces the densest clumps with so-called virtual planets or something like sync particles, and let those evolve, you can see what their masses are. And shown on the right-hand side are the virtual protoplanets that come out of this calculation as a function of their mass versus distance from the central protostar. This is a 1 solar mass protostar, by the way, compared to observations. You saw the observations really have not filled out this part of parameter space very well, but if these calculations are correct, these calculations would predict that there should be a lot more objects that Roman Space Telescope and microlensing might find in this region here. Now, the previous calculations started off, the ones that made clumps, started off gravitationally unstable. You might say, well, how do you ever get to such an unstable state in the first place? So these calculations now, a couple of years later, start off with a hot disk, very hot, 180 Kelvin, stable, but then allow the disk to cool down using sort of an intermediate value of cooling, which is a value that other people have found to be reasonable. What you see is if you start off hot, nothing much happens. You have sort of some axisymmetric rings form, but as the disk slowly cools down, once again, spiral arms form, you start getting very dense clumps here and there. If you replace the dense clumps with virtual protoplanets, again, you get this distribution here of objects versus compared to the observed. It's not intended to be a great match, because after all, these virtual protoplanets are just newly formed. They will continue to gain mass. They can go up in mass, increase upwards. They can also do all sorts of things in terms of migrating back and forth. So it's just sort of a proof of concept to show that these models are working on their way towards being able to predict what is actually seen in planetary demographics. Okay, what about our own solar system? Uranus and Neptune. So here's a model from 2003 with not a 20 AU radius disk, but a 30 AU radius disk, showing that if you start off with, again, the same sort of density profile, in this case, you can get 4 or 5 well-defined clumps. And I'm not quite sure why I chose this color scheme. I was not actually on acid at the time, but it certainly looks like a blacklight poster from the 70s. But it's very dramatic anyway. But how would you make Uranus and Neptune out of that? Well, George Wetherell and Nader Hakigipur and I published a paper showing that the idea is that even if you make those 4 gas giant planets, you can rely on photoevaporation of the disk to perhaps strip down the outermost ones and take a gas giant planet with a core and turn it into an ice giant. So for example, if you're in the Orion star forming region where there's strong EUV and FUV flux, disk photoevaporation is one of the favored ways for dissipating a disk. And around a solar type star with a 1/10 of a solar mass disk, it takes roughly 1,000,000 years to photoevaporate the gas and drive away and reveal the planets. Well, once the disk gas is photoevaporated away, guess what? The protoplanet, if it's out there, is going to get photoevaporated as well. So we did the calculation here and showed that on the same sort of time scale, 1,000,000 years, if you had a gas giant sitting out at 20, 30 AU, it's going to get photoevaporated down to an ice giant, to just whatever is in its core. So the table on the bottom shows how much mass you'd have to remove if you start off with, say, Uranus and Neptune with a 2 or 2.5 Jupiter mass protoplanet, and you take away something like most of that, you'll end up with the core masses, as core masses were thought to be back at this 20-year-old paper. So this is one mechanism for perhaps making ice giants. I should note that Saturn doesn't lose very much and Jupiter doesn't lose any, because it turns out that the distance of 5 to 10 AU, where Jupiter and Saturn are currently, is roughly the distance inside of which photoevaporation does not work, because the photoevaporation heats the gas to, it's basically forming an H2 region, it heats up to 10,000 degrees Kelvin, and inside 5 to 10 AU, that gas is still bound to the Proto-Star. So it's a natural mechanism for saying, hey, if you're inside 5 to 10 AU, you should not have lost much gas, but outside you're going to lose it. So that perhaps could explain Uranus and Neptune in this, this scenario. Okay, what about even larger disks? Here's some calculations. We're going out to 60 AU because I showed you earlier on there are a number of systems with very large radius disks. So I'll show you a sequence of different mass stars. Here's a 1.5 solar mass star, much like HR 8799, run for just a few hundred years. And this is a rather low resolution calculation. And you can see, well, here's 1, 2, 3, 4 clumps forming rather quickly. Lower the mass, and by the way, this doesn't have the beta cooling. This has real genuine 3D rate of transfer, so it's rather slow to run. It's very computationally intensive. Here's a star which is 3 times lower in mass, half a solar mass, still forming nice clumps, well-defined clumps. And take it down another factor of 5 to a 1/10 of a solar mass star, a late M dwarf. You'll notice that it's sort of petering out. You really only get maybe 1 or 2 clumps down here. So as you go to a lower and lower mass star, you might want to make the mass of the disk lower and lower as well. And eventually you're just not going to be enough mass around that disk to be strongly gravitationally unstable and form multiple clumps. So to summarize those models, here are the masses at several different times for the models versus from a 1/10 of a solar mass up to a 2 solar mass star. And in comparison, here are the 4 rough estimates of the HR 8799 system, showing that these planets are they're in the multiple Jupiter mass range. And as I noted before, they're only going to continue to gain mass most likely. And so they can go up and get closer to what's observed for the HR 8799 system. I should point out this paper was not designed to try to reproduce HR 8799 because I only really ran one model. So this is just sort of, again, proof of concept that indeed you can have disk instability form massive planets in situ at large distances. What about the semi-major axis as a function of the protostar mass? These are all, remember, the disk only extends from 20 AU to 60 AU, so they're kind of mostly forced to have semi-major axes in this region, although this particular one did end up with a much larger semi-major axis. And there was no, the planets weren't followed very far in time, so there wasn't any orbital migration inwards or outwards. But again, this is just sort of a proof of concept that these clumps that formed were not necessarily dissimilar from the HR 8799 system. Okay, so conclusions for part 1. As long as you have a massive disk, something like 1/10 the mass of the central protostar, then disk instability is a really rapid way, just a few orbital periods, for making clumps that could contract down to form gas giant planets. And at a range of distances from as close as maybe 5 to 10 AU out to at least 60 AU, or perhaps farther. I've not done models beyond 60 AU disk, but that's maybe something I'll do in the future. But I should point out, as I said from the beginning, that disk instability is just one end member. And in reality, probably a hybrid theory where you have both solids growing by pebble accretion or core accretion, as well as a gravitationally stable disk. That might be the way to form some systems in particular. And so at this point, this is a natural segue to the other end member. And so I now rely on the classic words of Monty Python. And now for something completely different. John, it's all yours.
Thank you, Alan. So if you want to stop sharing, I'll start.
Yep.
share here. There we go. All right, so following on from where Alan left off. So as Alan said, core accretion has traditionally been the favored scenario, although the jury is still out on whether it's always the case or whether both models have a place for forming giant planets, as Alan has described. So briefly, let me describe why a lot of people have tended to favor core accretion traditionally. And the main reasons are observations of the sun's giant planets, Jupiter, Saturn, Uranus, and Neptune, show that they're enriched in elements heavier than helium. And they probably have dense cores, centrally condensed regions, which could be objects that form in the core accretion scenario, as Alan pointed out, although we don't know much about the structure of them. And this artist's conception, which is shown in the figure here, is probably a little bit out of date now on the basis of the new Juno gravity measurements, which we'll hear more about in a few weeks from Tristan Guillot. But there is some evidence that the giant planets are enriched in heavy elements and may have a central core or a heavy region at the center. And it's also been favored because, although Alan pointed out one way you can make Uranus and Neptune with disk instability, it also naturally can explain their formation by core accretion, because both these planets, while they do have some hydrogen and helium, they're very much mainly made out of heavier elements. And so we can think of these as cores that formed and were just about to start growing into gas giant planets when their growth got terminated. And then also rocky planets are also formed in the same way. They form a solid object to begin with, but they never got big enough to grow into gas giant planets to accrete gas from their surroundings. So in some ways, it's a unified model for forming all different kinds of planets. Although, as we'll see in a minute, it's maybe not quite as straightforward as you might think. So why are you able to form a giant planet, a gas giant planet, when it's embedded in a protoplanetary disk? So, as Al alluded to just a few minutes ago, if you have a low mass planet in a disk, then its gravity pulls in the atmosphere, the surrounding gas, to form an atmosphere. But you get a stable situation where the outward pressure gradient of the atmosphere balances gravity pulling it inwards. But that situation only applies up until a critical mass. When you're above that mass, when the core is above that mass, it's no longer possible to find a stable solution. The pressure gradient becomes so high that gravity from the atmosphere itself starts to become important, because the atmosphere mass becomes comparable to the mass of the core. And gas always flows inwards as long as you still have a source of gas in the surrounding protoplanetary disk. And that critical core mass is something on the order of 10 Earth masses, as Alan pointed out, which at least fits with some early estimates for the core masses deduced based on the gravity of Jupiter and, to a lesser extent, Saturn, Uranus, and Neptune. So how do you form a solid object of 10 Earth masses if you want to do it the bottom-up process of banging the rocks together, pulling them in by mutual gravity to form a solid core, rather than going for a top-down approach, as Alan described? So a very simple way of calculating the growth rate would be a molecular dynamics kind of calculation, where you say the growth rate, dm dt, is the cross-sectional area of the planet times the relative velocity of nearby planetesimals, and the space density, that's the sigma over 2h factor. So sigma is a surface density or a column density. So if you imagine a disk, and you flattened everything down to the midplane and measured how much mass was in a unit area, that would be the surface density indicated by sigma here. So a very rough estimate for the surface density of a disk like the one that the sun's planet is formed in would be something like 10 grams per square centimeter of solid material at 1 AU, and then decaying very roughly as the inverse of the distance from the star, from the sun. And then at some point, temperatures will be cold enough for ices like water ice to condense. And so that bumps up your surface density by very roughly a factor of 2. So that's this F ice parameter here. When you do this simple calculation, you get rather long timescales, which are depressingly long, in fact. So to form a 10 Earth mass core at 1 AU takes of order 300 million years, and 10 AU, where Saturn is, it takes longer than the age of the universe. So obviously this is not the whole story. It has to be more complicated than that. And one of the missing ingredients is gravitational focusing. So in the previous calculation, we didn't take into account the gravity of the planet. When you think about it, if you have a planetesimal, that's the small object in the top of the diagram here, passing close to a large planet, the planet's gravity has a chance to alter the trajectory of the small object. And if the velocity of the small object is low enough, you can actually pull the object all the way into have a collision. And so the capture cross section is actually a lot bigger than the nominal cross section of the planet because of the planet's gravity, and that's called gravitational focusing. So when you redo that same calculation and you add a gravitational focusing factor, that's the term in the square brackets there, it boosts the cross-sectional area of the planet by this factor 1 plus the escape velocity over the relative velocity squared. So the escape velocity is the escape velocity of the planet. It's simply a measurement of how strong its gravity is. And then the relative velocity is how fast planetesimals are flying towards the planet when they're far away, so before the planet's gravity becomes important. And that is affected by different processes which can increase it and decrease it in a real protoplanetary disk. So every time a protoplanet and a planetesimal have a close encounter, if they don't actually lead to a collision, the trajectory of the planetesimal is still changed. You have a near miss, and that does a slingshot of the planetesimal past the protoplanet, and that alters its orbit. And over time, many of these encounters increase the velocity of the orbit relative to a circular orbit. So basically it increases the eccentricity or the inclination, the random motions of the planetesimals compared to a circular orbit. At the same time, these planetesimals are moving through a gaseous disk. Protoplanetary disk has gas in it, and that exerts a gas drag force which damps down these motions again. And that is dependent on the size of the planetesimal. So if you now factor all these things into the same kind of calculation I just did a minute ago, you look at how long it takes to form a 10 Earth mass core at 10 AU, so that's roughly where Saturn is today. It's a bit better. It's now down to 700 million years for planetesimals which are 100 kilometers in size, or about 20 million years for planetesimals which are 1 kilometer in size. So that is now getting towards the typical lifetime of a protoplanetary disk, which is a few million years, but it's still rather large. And as you can see, there's a strong dependence on the size of the planetesimal. And we have good reasons to think that planetesimals are probably big on the whole. So there's evidence from the size distribution of the asteroids in the main asteroid belt, and also the objects in the Kuiper belt. They have a fairly characteristic size distribution shown by this diagram here. And there's a kink in the size distribution somewhere around 100 kilometers in size. We think this is a relic of the primordial size distribution, such that objects which are above about 100 kilometers in size are mostly primordial objects. They're the original sizes of the planetesimals in the solar system. And the smaller sized objects are mostly fragments from the breakup of a few of these bigger objects. And you see the same size distribution in the asteroid belt and in the Kuiper belt and in the irregular satellites of the giant planets. It seems to be a universal size distribution for planetesimals in the solar nebula. And so if these objects really were about 100 kilometers in size, going back to the previous slide, you see the time scale is rather long, certainly too long to have formed the giant planets in the solar system. And in fact, it's actually worse than that. Because planetesimals have a habit of moving around. They don't stay where they first formed. This is a calculation by Al Leveson, one of the few calculations where he's put in all the dynamics in a fairly realistic model of planet formation. And he considered a disk of planetesimals spaced over most of the intermediate distances around the sun. So from a few AU out to about 10 AU, basically around the region where Jupiter was trying to form. And he put in a few seed objects. These are the green circles at the bottom of the top panel, and a smooth distribution of planetesimals, and then allowed them to run due to mutual gravitational interactions and gas drag. What he found was that while the seed planets scooped up a few of the planetesimals, they were much more efficient at scattering the planetesimals out of the region where they were trying to grow. So if you look at the bottom panel, the gray histogram shows the original distribution of planetesimals, and then the red histogram shows where they ended up. And while a few of them were accreted by the protoplanets, most of them were scattered out of the region entirely. And so planetesimal accretion is rather inefficient, because for every one that you capture, you probably tend to scatter several out of the region of interest. And so for these reasons, a lot of attention recently has focused on an alternative model for core accretion. It's still the core accretion big picture, but the details have changed now. And now, instead of the typical building block being an asteroid-sized planetesimal, the typical building block is now a pebble-sized particle, the kind of object you could hold in your hand, so millimeter, centimeter, decimeter-sized particles. And the reason why these have been the subject of much interest recently is because of the way they interact with a protoplanet during an encounter, when the encounter takes place in a protoplanetary disk. And that's because you have two processes operating at the same time. There's the gravity of the planet itself, and there's also gas drag as the pebble moves through the protoplanetary disk. And so you can get a range of different behaviors depending on the size of the smaller objects in the encounter. So if you look at the top left part of the diagram here, a traditional planetesimal encountering a protoplanet basically just feels the gravity of the planet, and it either collides with the planet or it flies past and doesn't collide with the planet. If you look at the bottom of the diagram, very small particles, micrometer-sized dust particles, are very tightly coupled to the gas, and so they tend to go where the gas goes. And the gas flows past the planet, and the dust particles get blown along with the gas and never have a chance to collide with the planet. And then in between, there's a sweet spot where the time scale for the encounter is comparable to the gas drag time scale, and so both processes operate. And while the pebble is approaching the planet, it's continually losing energy due to gas drag, and that greatly increases the chance of a collision as a result, and that's called Pebble Accretion. So here's a numerical calculation of this process in action by Lambrecht and Johansson a few years ago. What you're looking at is a region around a protoplanet, and the region where the protoplanet's gravity is more important than the star is marked by this red circle in the middle of the diagram. And then they fired a bunch of pebbles from the bottom of the diagram, moving vertically upwards in this coordinate system, subject to the gravity of the planet and also gas drag. And you can see that a lot of particles, even ones which are nominally outside the range of the planet's gravity, actually get swept in by a combination of gravity and gas drag. And so a lot of these pebble-sized particles can be accreted by the planet due to this process. Now, the different colored lines correspond to different pebble sizes. So you can see, depending on the size of the pebble, some get captured and others are moving on the same trajectory do not. And this process works best when the encounter time scale is comparable to the gas drag time scale, which is roughly centimeter-sized pebbles, depending on where you are in a gas disk. It's still effective for other sizes, but it works best for this sweet spot size. But pebbles, in addition to suffering gas drag when they encounter a planet, they also experience gas drag all the time as they move through a protoplanetary disk, and this means they move around a lot. So if the gas has any kind of pressure gradient, which it almost certainly will do, that affects the motion of the pebbles, and they drift inwards or outwards because they experience a headwind or a tailwind due to the pressure gradient. This is an analytic calculation done by Stu Weidenschilling a few decades back, showing how the different gas drag regimes affect particles of different sizes. When you're at very small sizes, you tend to move at terminal velocity, and when you're at very big sizes, you're mostly affected by your inertia. And then in between, at centimeter to meter sizes, again, gas drag is the most important, and you tend to drift rapidly, and you drift towards the nearest pressure maximum in the disk. So if you have a smooth disk where the gas is densest in the middle and its density and pressure decrease with distance away from the star, which is often the first starting point for models of planet formation and disk evolution, then the pebbles always drift inwards. They always drift towards the highest pressure, which is the pressure closest to the star. And that has a couple of implications for this model of pebble accretion. The first is that pebbles drift inwards and they drift past the planet or they get captured by the planet. The planet only has one chance to grab them. Anything that moves past it is gone. So the typical protoplanet will only be able to capture some of the pebbles before they've drifted inwards past its orbit. And that means you need a fairly massive disk in order to form giant planet cores, because the whole process is quite inefficient. And the second, potentially more serious problem is that when you look at what the lifetimes of these pebbles should be in a typical disk, they tend to be shorter than the actual lifetimes of the disks that you observe. And we know from observations of disks by ARMR and other instruments that pebbles are around in disks with ages of several million years, and yet simple calculations based on a smooth disk suggest the pebbles should be long gone by that point. Which brings us to a picture like this one, which is a composite of images similar to the one that Alan showed you earlier in the talk. Real disks have structure, they're not smoothly varying. And what you're looking at here are basically images of the distribution of pebble-sized particles fortuitously. And they have structure. They're arranged in rings. Sometimes they have spiral arms. Sometimes they have azimuthally varying structures. They're not smooth disks. That's the bottom line. And Alan suggested one possible explanation for this, which is that they could be caused by planets embedded in the disk. For the rest of the talk, I'm going to look at an alternative explanation, which is simply that they're intrinsic features of the disks themselves. And at this point, we just don't know which of those is correct. So what does it mean if you have disks with varying structure? And I'm thinking of disks where the gas pressure gradient varies with radial location in the disk. If the gas varies non-smoothly, then you'll have pressure gradients that change with distance from the star, and that will cause pressure bumps, and pebbles will drift towards the nearest bump in the disk. And Alan and Nada Hakikapur a few years ago actually did a study of this, where they found that pebble-sized particles will naturally drift towards these pressure bumps fairly rapidly. So here are calculations for a couple of sizes, 10 centimeter and meter-sized pebbles. You can see over timescales of a few hundred years, they will drift by considerable distances, so 1 AU in this case, towards the nearest pressure bump. So I'm going to show a new set of simulations from a paper I've just submitted about what happens when you try and grow planets by core accretion using the Pebble accretion variant, but in bumpy disks rather than in smoothly varying disks. And it has several advantages over all the previous calculations I've shown you. So these disks have intrinsic features. I'm not going to talk about what caused them. I'm just going to assume they exist because we observe them. I'm going to look at a fairly low mass disk. So a disk about 3% of the mass of the sun. That's the total mass of the solids and the gas. So a little bit larger than the minimum mass you need to explain the masses of the sun's planets. And 100 AU in radius is fairly typical for observed protoplanetary disks. And I'm going to consider a series of pressure bumps in the gas spaced radially logarithmically with distance and start one protoplanet in each of these bumps. And the initial mass of the protoplanets in the simulation I'm going to show you is roughly comparable to the mass of Pluto. So 10 to the -3 Earth masses. And what you're looking at here are 4 snapshots in time from this calculation. The time scale is shown in the top right-hand corner of each panel. The blue line shows the gas disks as a function of distance from the star, so you can see the wiggles or the pressure bumps. And then the green line are how the pebbles are arranged in distance. The surface density of the pebbles is a function of distance, and pebbles are added to the model slowly over time to account for how long it takes the pebbles to form from smaller dust grains. You can see the pebbles quickly adjust to the distribution of the gas and form peaks fairly close to the peaks in the gas distribution. Then the red dots are the protoplanets, one at each bump, initially 10 to the -3 Earth masses. And they grow very fast in the outer disk, as you can see in the lower left panel. After 250,000 years, you've already approached Saturn mass for 2 of the protoplanets. At this point, their gravity is strong enough to start to open up gaps in the gas disk. That's why the blue curve changes. And also, these changes in the gas disk strongly affect the distribution of pebbles. And so the pebble distribution also changes. Whereas in the inner disk, the planets remain small, comparable to their initial values. So part of the reason for that is that the outer disk and the inner disk behave differently. And in the outer disk, some of the bumps are able to trap pebbles. So if you look at the diagram in the bottom right here, the curves show the radial velocity of the pebbles as a function of distance from the star for 4 of the bumps in the previous figure. Values that are positive above the dashed line are radially outwards, and values below the dashed line are radially inwards. And the circles mark places where pebbles will naturally tend to accumulate, where there are pebble traps. The different curves show what happens if you just consider the pressure gradients in the disk, or if you also consider the inward motion of the gas, which also tends to push the pebbles around. And when you consider both of those, you only get pebble traps forming at some of the bumps. That's the blue curve, and you see in the inner disk, you don't get traps. In the outer disk, you do get traps. So when you look at the how the pebbles change over time, that's the top left figure. This shows again the surface density at 4 of these bumps over time. And in the inner disk, the surface densities go down because there is no trap there. The pebbles are lost, whereas in the outer disk, the pebbles can survive at the traps. And that allows the planets to grow much bigger. The outcome is also very sensitive to the mass of the initial seed body that you put into the calculation. So here are 5 calculations looking at different initial seed masses for the planets. So the top diagram is the one I showed earlier, where the planets are a little bit smaller than Pluto to begin with. And then the middle diagram shows objects which are about the size of Ceres, and the bottom diagram is more like the size of Vesta. And you can see just changing the initial mass by a factor of 30, which is about 3 in radius, is the difference between forming a set of 4 giant planets or no planets at all, no giant planets at all. And it's equally sensitive to the turbulence level you put into the disk. Very sensitive to these small changes, which naturally would give rise to very different systems, in different outcomes in different systems, depending on the initial conditions and small changes in those initial conditions. And the last thing to consider is that the planets migrate. They do this because the gravity of the planet changes the distribution of the gas in the disk. And this is a calculation by Pavel Artimowicz showing that. This is, I believe, a 3 Earth mass planet in a disk. And it's color-coded by the density of the gas. And you can see it launches these spiral arms, where the gas is overdense compared to the rest of the disk. And then the gas in these arms pulls on the planet and changes its orbit. And actually calculating how it behaves is rather complicated because some parts of the disk push the planet inwards and some parts of the disk push the planet outwards. But the net effect is usually, but not always, inwards migration. So here are how the 4 planets in that simulation I showed earlier migrate for 2 different migration models, which probably bracket the end member possibilities. And you can see there's always inward migration, but in some cases it's quite modest. It tends to be less of a factor in the outer disk than in the inner disk. So planets in the model always form in the outer disk, but sometimes they can migrate into the inner disk, which may be an explanation for some of the hot Jupiters that we see. So to conclude, for the reasons I described earlier on, giant planets far from their star are unlikely to form by planetesimal accretion, and even forming Jupiter and Saturn is tricky by planetesimal accretion. Pebble accretion is a much more promising route to form these planets. It's potentially much faster, although it is inefficient. So you need a massive disk to do this. But if you have a bumpy disk, then that overcomes that inefficiency because the pebbles can be confined at traps in particular regions. And as long as you have enough pebbles in one trap to make a planet, you'll tend to do so. And you can form Jupiter-mass planets to at least 60 AU, so that's comparable to some of the systems that Alan described earlier, within 3 million years, which is a typical disk lifetime, for a fairly low mass disk. So this may be one channel for forming some of these objects, although, as Alan pointed out, it's not necessarily the only channel for doing that. But the outcome is also very sensitive to the conditions that you choose. And this may explain a good deal of the variety between one system and another. Very small differences in the initial conditions can lead to very different outcomes. Okay, that's all I have.
Okay, silent claps from everybody. Those are great talks, thanks. So I have one question for Alan, one question for John, and then we'll open it up to others. First is Alan, so just to finish off what John was saying, disks are not smooth. Disks could be clumpy due to snow lines, different volatiles evaporating at different places. So my question to Alan is, when you run your models, are your disks usually smooth, or do you include clumpy disks?
Good question. When I run the models, I start them smooth because that's why not? They're going to become clumpy, and if they're gravitationally unstable, they will rather quickly form rings if they're not really quite unstable enough to go completely nuts. And if they're unstable enough, they will form spiral arms that come out of the rings. And so that's one of the reasons why Nader and I published that paper that John referred to about having particles move to the pressure bumps, because I was already thinking back then, well, listen, if you have a disk that's doing some gravitational instability, whether or not it's going to make gas giants directly, it's certainly going to affect the particles. And so you're going to get pressure bumps that John talks about. In fact, Colin and I, we've been doing some modeling of trying to understand how CAIs, which are roughly centimeter-sized particles, evolve in the nebula. And so we've taken some of my gravitational instability disks and put centimeter-sized particles in them and see what happens to them. And they do tend to get clumped into the spiral arms which are coming and going. We often see enhancements of a factor of 10 or 100 over the background density of the CAI. So we really would like to go ahead and continue those calculations and really truly merge them with the sort of things that John's talking about. That's why I say, you know, a hybrid theory might work for at least forming some systems. But no, you're right. Pressure bumps I think are going to be there. I think the real question is whether or not how massive the disk is. So if you're massive enough, then you're going to have those pressure bumps for sure. If you're low mass, then as John says, you know, who knows? Then you sort of have to go back to Jehan Bey and his folks who are looking at the disks that ALMA sees and try to interpret what's actually going on. Have planets formed already, or they're not formed yet? So still lots of questions there.
Okay, that's the second kind of question I had for you, Alan, maybe also Alicia, if she's still there. I don't know if she's still online or not. But do we know how disks mass varies with a star's mass? Do we know that the smaller a star is, the disk is significantly less massive?
I think to first order, the disk masses scale with the stellar mass. Certainly low mass M-dwarf stars still have disks that are at most maybe a tenth of their mass. But in most cases, determining true disk masses is very hard because we're not really measuring the molecular hydrogen, or which is where all the mass is. So one's always guessing, trying to convert something like some proxy for the dust grains and converting that to how much hydrogen should be there. Disk masses are still highly uncertain. In fact, most people would say that most protoplanetary disks are not massive enough to be unstable. Only a few are maybe up at 10% of the solar mass. So that's something where people are still actively working on them, but with ALMA observations and getting ranges of disk masses. But certainly they do scale with stellar mass, but more or less proportional to the mass of the star.
Okay, and another question I had is for John. I don't know if Alan might answer this as well, but when I was in school growing up, there's always these problems of making Uranus and Neptune at their current distance. So a lot of people believe they formed closer in and got pushed outwards. With current pebble accretion and other ideas now, can Uranus and Neptune form where they are fairly easily, or is that still a problem?
I think as long as you have enough pebbles, you can form them pretty rapidly. The issue may in fact be, why do they stop growing? Why don't they accrete massive gas envelopes like Jupiter and Saturn? Do you require fairly fine tuning in the timescale to form them just as the gas is going away? Or is there another mechanism that stops them growing larger? So I think with pebble accretion, you can form them where they are now. The question then becomes, why did they stop growing? Why didn't they accrete massive gas envelopes like the other giant planets?
Yeah, I think we should ask Matt Clement to comment on this too, since he's worked very much on trying to form the present solar system planets, outer planets. Matt?
Yeah, the ice giants are a problem. I think, one thing that has to be accounted for too that we haven't talked about is their high obliquities, which hint at possibly some giant impacts. So their formation might have been slightly different. We also think there might have been some more of them that got lost or got tossed around. So yeah, that is the missing link.
Yeah, I mean, if you look at their dynamics, their eccentricities or obliquities, like you mentioned, Matt, it suggests that they didn't form where they are, or some serious things happened to them. I guess in other star systems, do we expect there to be ice giants, kind of like we see Uranus and Neptune, based on dynamics or based on how they formed? And I think like 10 years ago, I think the obvious answer was Uranus and Neptune got pushed out there. But I think now, at least as far as I can tell, is that Uranus and Neptune likely got pushed out there. They formed closer in where it's easier to form, but they may have been able to form out there if needed. Is that correct?
I think you're going to have a heck of a time forming them where they are now by planetesimal accretion. But I think you can form them where they are now by pebble accretion. You can at least form their cores. What happens after they've formed a critical mass core is an open question.
Okay, and so we'll open up for questions from others. I see in the chat from Harold Williams, he's asking how turbulence is handled in your guys' calculations.
So I replied to Harold that in my models, the disk instability itself produces a chaotic phase of motions, which I've estimated is equivalent to a classical viscous accretion disk alpha of about 10 to the minus 3. So turbulence is not put in. It's something which arises naturally from an unstable disk.
So in the calculations I showed you, it's parameterized by a quantity called alpha, which is a measure of the strength of turbulence compared to the motion around the star of a normal orbit. So the calculations I showed had a turbulent alpha of 10 to the minus 4, which is at the low end, the values that are often considered. And the main effect of that is to affect the motions of the pebbles and the protoplanets. So it stirs up the pebbles to make the thickness of the layer in the midplane thicker than it would be if they just settled by gravity alone. And it also causes density fluctuations in the gas disk, which can then perturb the orbits of the protoplanets. And that's the reason why the outcome is very sensitive to the mass of the planet in the outer disk, because the relative strength of the turbulent excitation compared to the damping caused by the gas is sensitive to the mass of the planet. So it's put in a parameterized way, but it's based on the results of more detailed calculations.
Okay, Connell, you have a question?
Just quickly, John, what happens to Pebble accretion once you the planet launches a spiral density wave? Does the dust get focused onto the density wave and make its way into the planet, or does it get stuck in the density wave and that's the end of Pebble accretion?
That's a good question, which I don't think has been entirely explored. What I can say is that once the planet, once the gravity of the planet is strong enough to affect the radial distribution of the gas, once it starts to open up a gap, then you get a pressure bump outside the planet, and that stops the pebbles drifting inwards. Most of those calculations are 1D radial calculations. They don't consider the spiral structure. And I think relatively few calculations have actually looked at the 3D motions of the pebble. So that, I think, is still an area of ongoing research.
Yeah, I just wondered if there was a self-limiting process there, that once things get big enough, you stop, Pebble accretion ceases.
Certainly, if you start to open a gap in the disk and you make a pressure bump outside the planet's orbit, which will happen at some point,
yeah,
that certainly will shut off Pebble accretion. And that's been one of the ways that people have thought of as a way to stop the cores growing too big so that you can then start to accrete gas. But exactly what that mass is still somewhat uncertain.
So
Okay.
Jay put in the chat a reference for a paper about disk mass versus stellar type. Jayhan, could you quickly summarize what you saw from that paper you put in the chat window?
Sure, yeah, I can do that. I guess the title already says the answer. The title is a steeper than linear disk mass, stellar mass scaling relation. So what that means is that your star is more massive, then you get more massive disk. Although, as Alan pointed out, this particular study is based on ALMA continuum observations, which is meaning that you are looking at dust component of the disk, which is in mass, dust is about 1% of the total disk mass. Everything is almost, in H2, and we don't really know, we don't have, good measure to infer the H2 gas mass. So we either use usually continuum mass, dust mass, and then multiply 100 to estimate the gas mass, or we use CO lines. So we get CO mass, and then using CO to H2 ratio, abundance ratio, which is, of course, has a lot of uncertainty in it, and converts CO mass to H2 mass. So yeah, I guess I would say that, yeah, if you have more massive star, you'd likely get more massive disk, but there are a lot of uncertainties.
Yeah, and that's measuring, yeah, like you said, there's only certain things we can measure. And so it depends on what you can measure, and there's a lot of hidden things there, right? So it's hard to get at.
Right.
Okay, do we have any more questions for our speakers?
Actually, I've got one for John.
Okay.
John, so in your new models, the 2021 paper where you have the gas with the bumps in it, you have using a 1D viscous accretion disk model to let the disk gas evolve. Is that how that's handled?
It's actually even cruder than that. It's assuming a surface density with a fixed profile, that's the bumps. But then the scaling factor, the absolute value of the gas mass, decreases exponentially over time. So it's deliberately a very simple model in order to get a good picture of what the bumps themselves is doing. the next step would be to do a more realistic viscous accretion model.
Yeah, well, I was impressed when I saw the bumps evolving. I was wondering, ooh, that's pretty cool. Because I would have thought step one might have been just fixed bumps, but you went well beyond that, clearly.
I mean, most of the changes are due to the fact that the planets themselves are opening up a gap, and that is also parameterized based on hydrodynamic calculations of how big a planet opens up how big a gap.
Well, also notice, John, you put in quite a few bumps. You put, I think, 8 bumps in. I don't know how big your disk was there, if that was a 3040 AU disk, but you expect more bumps or less bumps? And why did you choose that number, I guess?
Well, I chose a disk that started off at the orbit of Mercury and went out to 100 AU, which is a typical disk radius. And I had the bumps spaced by a factor of 2 in distance for each bump, which makes 8 bumps. And that's roughly the kind of distance between some of the bumps you see in the ARMA observations, but they can't probe the inner disk, so you don't really know how far in the bumps extend. So the ARMA disks, you see 2 or maybe 3 rings, so 3 bumps. But if the bumps extend into the interior, you might get more than that.
Maybe we could ask Jay Han to comment on to what extent ALMA may not be able to resolve all those bumps. I mean, we have limited resolution. We're happy to see 3 or 4 bumps in some of the disks, but Jay Han, what do you know about that?
Yeah, so technically, the highest angular resolution you can have with ALMA is 0.02 arcsecond, which means that the nearby star forming region, which is about 140 parsec, right? Like Taurus of Eucus, those star forming regions. So that gives you a linear resolution of about 3 AU. So I would say at Jupiter radius, orbital radius, you can pretty, well, not easy, but you can relatively easily resolve if there are any structures. But if you go, inward of Jupiter's orbit, then I don't think you can really tell much about the structures.
Yeah, and the bumps are, it's a chicken and egg problem to some degree, right? We don't know if the bumps are there before the planets or because of the planets, right?
Right. That's a big question at the moment, and that will have a big impact on what's going on.
Could I continue with breaking tradition by asking another question of the audience, namely Johanna? What does she think about the effects of metallicity on giant planet formation?
What do I think? Like, is it having an effect or not?
Yeah, just comment generally on how the old metallicity argument seems to have evolved quite a bit.
Yeah, I agree it has evolved. I think in the plot that you showed, the more recent plot, that probably includes not just giant planets. Is that correct? It was all planets. And so
it's everything. Yeah, everything.
Yeah, so we now have pretty clear evidence that the correlation decreases and maybe even in strength and maybe even goes away for the smallest planets, kind of the super Earths and some Neptunes. Although, yeah, that whether it is totally gone or just weak is a little bit fuzzy. But I think at least for the close-in giant planets, there's still a trend there. But kind of 2 areas that I think I'm interested in exploring more are the longer period giant planets. And I think there's been a few papers recently that have pointed to the metallicity trend not holding for longer period giant planets. And then also really pushing to the lowest metallicity regimes and seeing what planets are there. Those stars have been avoided for various reasons in surveys. Yeah, that's a project I'm interested in. Kind of how low can you go in terms of metallicity for forming any kind of planet?
Thanks, Joanna.
Thanks. I hope you're not actually driving there. That's just a picture you took when you're driving, right?
I'm not.
Okay, I don't see any other hands. I don't know what if we're actually planning to continue on with something here, or if that's the end of this talk. I don't know. I think Alicia sent something out about postdocs are talking with the speakers or not. I'm not sure if that's happening. Is that something you guys want to do?
Well, I'm getting ready for lunch, I'll tell you that.
If there's interest, I can stick around.
Oh yeah, I think yeah, I mean, my thought was, if anyone who has questions can ask them now, but otherwise, I think we can go wait until next week for the next talk, which will be by Scott Kenyon, and talking about Pluto's satellite systems and how a lot of the dwarf planets out in the outer solar system are found to have satellites, and we think they're from collisions. So collisions are a heavy, important process for forming a lot of these dwarf planet type objects. So we'll be talking about that next week. So thanks all for coming out. Very much thanks for Alan and John for giving excellent talks and keeping us up to date about how these planets form. It's a very hot